alkenes are useful synthetic intermediates. Their double bonds can undergo a variety of chemical transformations, providing useful functional groups like halides, alcohols, and carbonyl compounds. Let's review some of the major reactions that alkenes undergo. An alkene can be reacted with hydrogen gas in the presence of a metal catalyst to produce alkanes. The hydrogen gas adds to one face of the alkene, so we get syn addition of H2 across the double bond. Alkenes react with halogen-containing acids like hydrochloric and hydrobromic acid, adding a single halogen across the double bond. If the alkene is reacted with acid in the presence of water or an alcohol, the result is an alcohol or an ether. Water or the alcohol can be used as solvent in this reaction. You may have noticed these reactions are regioselective. In our example, the new functional group is added to the central carbon and not the terminal carbon of the alkene. This is because these reactions form a carbocation intermediate. The more substituted carbocation forms because it is more stable. Because carbocations are trigonal planar in geometry, they can be attacked by the nucleophile from the top face or the bottom face. So if there is a stereocenter produced in the reaction, it will be a mixture of R and S. When this happens, we say a racemic mixture is produced. The addition of the nucleophile to the more substituted carbon of the alkene is sometimes referred to as Markovnikov addition and is related to carbocation stability. Rearrangements via hydride or alkyl shifts are possible with these acid-promoted reactions. Treatment of an alkene with liquid bromine or chlorine gas adds 2 atoms of the halogen across the double bond. And if the reaction is carried out in water, a halohydrin is formed. The latter reaction is again regioselective and stereoselective. A bromonium ion forms, and the nucleophile attacks at the more substituted carbon atom because there is significant contribution of the more stable carbocation resonance form here. This accounts for the regioselectivity. The functional groups are also added to the molecule stereoselectively. Because the bromonium ion blocks one face of the molecule, the nucleophile must approach from the opposite side. We call this anti-addition. Allylic bromination is a radical reaction that adds a bromine atom to the carbon adjacent to the double bond while preserving the alkene functional group. Oxymercuration also forms alcohols from alkenes in a Markovnikov fashion. A mercurinium ion is formed, which reacts with water at the more substituted carbon atom. Treatment with sodium borohydride reduces the mercury, removing it from the molecule. The major advantage of this reaction is that carbocation rearrangements by hydride or alkyl shift are not possible, although mercury is a rather toxic element to use in the lab. Hydroboration-oxidation forms the less substituted alcohol via non-Markovnikov addition. Boron is often substituted with large R groups to make this reaction more selective. Examples of commonly used reagents are 9-BBN, dicyamal borane, and borane THF. The large boron group adds to the least sterically hindered side of the alkene, while the small hydride atom is added to the more substituted carbon atom. Treatment of the boron complex with sodium hydroxide and peroxide in a second stage of the reaction produces the alcohol. The addition of 2 hydroxyl groups across the alkene is accomplished by treatment with osmium tetroxide, which forms an osmate ester. This reaction gives a syn-diol because osmium approaches from one face. 1 molar equivalent of a reducing agent is required to cleave osmium from the molecule and produce the diol. Ozonolysis essentially splits a double bond in half, creating a carbonyl compound from each side. In our example, a substituted aldehyde and formaldehyde are formed. We need to take a look at the mechanism to understand what is going on here. The addition of ozone forms a malozonide, which rearranges to form the ozonide. In a second step, dimethyl sulfate is added. This cleaves the oxygen-oxygen bond, and the charged intermediate collapses to form carbonyl compounds and dimethyl sulfoxide. The Wittig reaction is an alkene-forming reaction that seems relevant to touch on here. A carbonyl compound is converted into an alkene by treatment with an organophosphorus reagent. This Wittig reagent is a phosphorus ylide. Although we can draw a resonance structure with a double bond, there is also contribution from a neutral dipolar form. The carbanion form makes it a bit more apparent how the carbon atom of the Wittig reagent ends up bonded to the electrophilic carbonyl carbon of an aldehyde or ketone. The side product of this reaction is triphenylphosphine oxide. Z-alkenes are favored under the classical Wittig conditions. When there is a possibility for resonance stabilization of the carbanion, the E-alkene is more favored. Alkene metathesis, though a bit more advanced, is an important reaction in modern synthesis. Treatment of two alkenes with molybdenum or ruthenium catalysts result in the formation of a new alkene with substitution from the original alkenes on either side of the double bond. This reaction is most useful when it is done in an intramolecular fashion to close a ring.